So this topic is the last topic that's on the exam. This ain't hard, so don't make it hard. You're going to have some exercises that are going to look very familiar on the test. You're doing them now. So what we're doing with hashing is that we're trying, notice I said trying, to search for something in close to constant time. Now notice I say close. It won't be perfect, but it'll be pretty damn good if the application and how you apply it is correct. So there are some caveats to this. Not everything works with this. But we're trying to basically find a certain value in a huge data set within a very short and damn near constant time. This requires several things. Two functions. You have a hash code, which I'll go over, and compression. And then the overall process you see on the first page there, I'll go over that in detail here in a minute. But you also have a lowercase n and a capital N, and be careful about the difference between the two. And again, I'll go over it, but n is lowercase n is a number of total keys or values that you're going to store, and the capital N is a number of buckets. So what do I mean by that? Woo, too fast. So what I'm trying to do is I'm trying to find a person out of 319 million-ish people that are here in the United States. I don't know exactly where this person is, but I'm going to try to find them quickly. So the first thought was, okay, well, why don't we break this up into buckets of states? This sounds like a good idea. You can break it down into 50 different states, and we just look at the 50 states if we need to. The bad part is that if we look at the demographics of the states, it's not an even distribution. Notice California, pretty big compared to Nebraska. So what we're trying to do is we're trying to find a capital N, which is a number of buckets, that would support an equal number of keys, an even distribution throughout all of it. Here's a better example. How many of you ever played with Legos? Okay? Now, when you play with Legos, other than it getting somehow stabbing pain that it causes when you step on one, what were some of the ways that you organized your Legos? Let me stop there. How many of you actually organized your Legos? Okay, yeah, see, now you know why I stopped and did it this way, okay? Personally, me, I am one of the official Lego builders myself. I have probably close to 500,000 bricks. It sucked to move them. They're heavy. How did you organize your Legos? Sorry, buddy? Colors. Okay, who else? You're back. What did you organize them as? How many dimples they had? Yep, or studs. Mm-hmm. Okay, what else? I think there's somebody else over here, too. Okay. Type of brick, yep. Mm-hmm. Okay, very good. Now, for me, it's funny, I did all three. Because also I have 500,000 of them, too. It's by color, and broken down further. It gives us a nice, even distribution when it comes to Legos. So that's the key ingredient about this, is not just how are we breaking them into buckets, but are the buckets going to have an even distribution? Because remember, I'm trying to find something fast and about consistent near constant time. Again, near constant time. So if you have a bucket like California, that's going to skew everything. That means you don't really have a great setup. Now, sadly, for the rest of them, they're not too bad, but California kind of whacks things. I think, is New York on there? New York has a very high population, too, and so does Texas, obviously. So, and I don't think Texas is on there either. So there's a couple of big boops and blips that, frankly, doesn't make it worthwhile. So we want something called a uniform hashing assumption And this is what we try to do, is we try to actually figure out, divide our total number of keys divided by the number of buckets, and that's what we're hoping it'll be about an even distribution of. That makes sense. Just a very simple division. Doesn't always work out that way. So, because again, in real life, California's got a much bigger state. So, here's how we're going to do this. Big picture. The big picture on this is that what we're going to do is we're going to look at one part of the value called the key. And remember, this data set could have many more things than just the name in it. It could have their social security number, how much they owe, bank accounts, all that stuff. But we look for just one value in the data set. That's it, called a key. We translate that key into a bucket, and then that bucket is going to hold that value with the rest of the data. Now, what I want you to look at is actually towards the middle. You see where John Smith is? And then there's a link that goes below it to Sandra D. We're not going to get a one-to-one in reality. Let me put it this way. We're not going to have, let's put it this way. We're going to have what is called collisions, meaning that one bucket is going to house several values or key values in it. It's just the way it is, okay? Otherwise, if you do one-to-one, then you still have your function being credible over spinning it all out, and also, frankly, it may not be worth the time. So you are going to have some collisions with, like it says, John Smith and Sandra Lee. Now, the key and the value. So, excuse me. So in the example that you see right here, none of the data is actually changed, but what it does is it pulls from the key that we want, it'll go into a hash code, then into a compression which says, okay, hey, I don't have 319 million buckets. I've got 50. So I'm going to compress you somehow into 50 using our modulus operator, which you probably haven't seen that in a while, and then pick that bucket to contain that data. Now here's the good news. That compression and hash code functions are used over and over again, not just to drop data into a certain location, but also to tell you where it is. Because the data once dropped into a bucket is not going to be moving. Because again, the overall goal is to find something fast. So those two functions are going to look exactly the same when we're dropping items in and when we're trying to find an item. So we have seen this before in games of tic-tac-toe, and that would have been a great project, but I didn't do that one. But whereas you may have different aspects, it's a multi-tiered hash table of, okay, well, they went X in the upper right, well, we go to that bucket. And then, okay, now they go to the next bucket underneath that has 9 different options. So that is one example of that you could use for hashing, but again, I didn't torture you with that one, but just a couple of examples that just come up. Collisions and probing. These are two terms that also come up in hashing. Collision, which I've already talked about, is when several keys hash into the same bucket. So again, what you'll see in front of you is you have theater and music. We had a collision. That's fine. Collision's not bad in this case, but they're both housed in the same bucket. Probing is a different topic, but it means exactly what it's saying. Probing means how many times does it need to look for a spot in order to find what you're looking for. Probing also may mean, depending on the algorithm, if it doesn't like collisions, okay, what is my next spot that's empty that I can drop an item into? Now, I haven't shown you that example quite yet, so bear with me. But those are different examples of probing. Probing is literally searching for either a spot to drop off new data or searching for that new data. But it's always the word searching more than anything else. All right. Now, one of the types of ways of handling collisions is called chaining. And chaining is exactly like using a linked list. Here we've got 2 keys, store and store, matter of fact, but notice they have 2 different values or data definitions, really, in this case. but they're both stored in the exact same bucket. That's chaining things together. That's what most of our items are going to have. Now, here's the bad news, and I'll be straight up honest with you. Your book, and when you're cheating online, they show you other examples too of different algorithms of hashing. Most of them that are in real life applications are going to be using something like this. Because how many of you are familiar with linked list? Raise your hand. Very good. How many of you would rather, how many of you would rather say, hey, look, just put it into that spot now instead of looking for a new spot with serving 50 million pieces of data? How many of your people are lazy? Raise your hand. Yeah. This is mostly going to be this application and setup. But the book does use different examples. It's not yet, but I'm showing you the chaining example that it shows in the book. So, excuse me. So here it's giving you the hash function, which is the h of k, and k says k is the mod of 10. And the mod 10 is actually your compression function with it. So n, capital N, is the number of buckets. So for discerning values in, like we have here, 12, 18, 30, 13, 2, 3, all that good stuff, we would then send it to the hash function, which says, hey, I just want you to give me the remainder by 10. So 12 mod 10 gives us a remainder of what? 2. So notice 12 gets put into the 2 spot in the hash table. Then we get to 18. 18 mod 10 gives a remainder of 8. So notice it's in the 8 spot. And then I think you can figure out the rest of that. Now notice it's chaining because I have other values connected behind it. Now, oh good, okay, it's already there. Yes. I want you to look at the question at the very bottom. If the data portion was a linked list, why would inserting at the rear be inefficient? Why? You have to assume a few things. Yes, ma'am. Perfect. You need to write that down somewhere. If you don't have a rear pointer, you would have to iterate through the whole darn thing and then drop your value. So that would take, obviously, more time to drop it off. So if you don't want to assume that it has a rear pointer, what's the easiest thing to do? Just drop in the front. And that pushes everybody back. Not really pushes everybody back, but just drop in the front. Now, that's what your book assumed, and I did not want you making that assumption. Okay? Even though you and I, when we went over linked lists, we talk about rear pointers and stuff like that, you might get another class where they don't do it that way. That's fine. So to be safe, in reality, it's going to put the new chained value in front instead of traversing through the entire list just to get to the end and dropping it off. Everybody okay with that idea, though? Is there any questions on that? All right. So here's what I want from you. Here's our first chaining exercise. So all I want you to do is notice a couple of things. Number one, the buckets is 13. Number two, a hash function is k mod 13. So all you're going to do in this chaining example is put those values in the correct order. Now be careful. If you have a chain, or excuse me, if we have a collision, where is that number going to go is really, really important. I'm going to ask you to do up to 37. So that's almost half the numbers. I don't want to go through all of them. I want you to go up to 37. This should not take long. This is why you need your calculator. Do the mod of 13. You figure out what spot it's in. That's it. Draw it. Boom. Move on. But you need to draw it out and go from there. Get to work. All right, let me see your faces. So by the way, some of you are scaring me with the, yes, even back in my day, I was using the TI-83s, 81, stuff like that, which still some of you using them. Frickin' this one that made her a drink. I don't know what type of TI that is, but anyway, it's the first time I've seen that one. So you're going to need your calculator. I do not want you using your cell phones on Thursday. Okay? Bring a calculator. It doesn't have to be her $3,000 one that's probably more worth than a Mac. Okay? But it can be a simple one. Now, I want you to look at the answer that you see in front of you very carefully. Now, again, I only asked you to do some of the numbers. So does your answer match the one that's right in front of you? Probably not, because you didn't do all the numbers, and that's fine. I'm not worried about that. Here's what I am worried about. Is that if we had a new number that collided at index number 3, we had a new number that collided at index number 3, and we say collided because there's already one there. It looks like it's 81. If the new number is 23, who's going to be linked first? The 23 or the 81? It's going to be the 23. Now, we've got to be careful about this, so listen to me carefully. I've had people do this answer, and the links were completely the opposite way. Was the answer right? No. Order matters. So be careful while you're doing this on the exam. Order does matter. So be very, very careful. Okay, next one. Now, like I said, I'll always be honest with you. The next few are great to talk about, but practical, I don't know. So hang on, sorry, I'm getting to the damn thing. Sorry about that. There we go. The next one that we talk about is called linear probing. This one, the example of the states one is a good one. Here's the only reason why. Because you knew the distribution with the number of buckets wasn't going to be even. This one makes sure it is. Because here's what it does. If it finds a collision, it then looks to the next spot up to see if there's an empty spot. If it's not there, then it goes to the next empty spot. And then the next empty spot. And then the next empty spot. And it keeps going, and it actually wraps around until it finds an empty spot. Now, some of you are going, wait a minute, what if there's not an empty spot? Great point. You would have some data member in there letting you know, okay, is it the next level now to go and attach the next one? So you would still have some chaining involved, okay? So that would be a data member. Very simple answer to that. So let's pretend the whole damn thing is full, and we got a new number to put in there. Our level variable say, okay, 1 is done. We put it in the spot, look at our data, say, okay, well, now we need to add level 2. So not trying to make this hard. And again, this is more educational than it is realistic. Yeah.
If we move the data member from the bucket we were going to originally put it in after using our hashing function, does that mean that when we want to find it again, we can't use our hashing?
Well, no, we would look at our hashing function and say, oh, well, damn, it's not there. Okay, so what do I do next? I move up 1. The exact same thing as we did to insert it in there. Okay, same exact thing. Okay, so yeah, no, both hash functions used twice, inserting and finding. All right, now, so here's your linear probe example. Now, I forget which number it is. It's not 12, 18. Okay, so I want you to look at, I want you to highlight for me the value number 2. So go over here and highlight that value number 2 if you would for me, please. Now, why I'm having you do that, and I'm going to draw it on the board here, is that if I'm doing this from left to right, and again, I'm modding it by 10 just to keep it simple here. 12 mod 10 is 2, so there's that one. No big deal. Filled in. 18 is 8. That one's done. 13 is 3. That one's done. 2 mod 10 gives us a 2. Uh-oh. 2 is already filled in. I can't use that spot, can I? Now, what do? I go to the next one. Uh-oh. That one's full. What do? Go to the next one. That one was empty, and that's why I can get away with putting a 2. Everybody okay with that, though? So notice, all I did was increment by 1 to find the next spot. Now, I think you can realize, well, geez, that increment by 1 could suck. You're absolutely right. That's why, again, there's fewer applications for this than just using the chaining. All right, so let's see if you're good at it. Same idea, different. I think it's the same data set, if I'm not mistaken. This time your N is 29. So have at it. Watch how you are probing to find your next available spot, and then go from there. I am showing you the full answer on the very bottom of the screen that you have in front of you. Now, this time, your work should actually coincide with it. You may not have filled out every single element in the array. That's fine. But it should, whatever you did get done, should be in the right spot. There's no pushing things around or anything else like that. So, honestly, again, even if you didn't complete, your numbers should be in the right spot. So please take a look, and we'll move on to the next one here in a second. Now, like I said before, but apparently some people didn't hear me, this is theoretical. Why would you want to use this? You wouldn't. Let me make this clear. This is only an educational thing because of the next one. Excuse me. The bad part is in the previous one, you have something that's called clustering. And clustering means that you have to constantly increment by 1 by a lot to find the next spot. And how is that good or bad? That's bad. So we did that one because of this one. This one, I didn't have any other better term in the years I've been teaching this other than it spreads the love. Meaning, it doesn't put data one after another like the previous one. Remember, the other one just incremented 1, oh, found a spot, done. This one actually uses a quadratic formula. It's very simple, so we don't want to go that far. Of trying to actually spread out the data. Now, here's the bad part. While at first it sounds great that if you have a large number of buckets, it tries to put data kind of spreads throughout. But what if your buckets have 1 available spot left? And he said, that's a bitch. You're right. Because you hitting that spot, I'm going to call it a hole for right now because there'd be a hole in the data. You hitting that last hole in the data for that level will probably take a while. So yeah, there's bad parts about this too. So let me show you how this works. So in this one, it's called quadratic because what I do is, it's dumb, but it's easy. That's the good news. I use a quadratic on my incrementation or how many times I've tried to find a spot. Let me explain. So if I am looking for 89, I do a mod 10, I look for space 9, oh, there's nothing there, beautiful. Just drop it right in that spot, no big deal. Okay, my next number is 18. I look at the 18th spot, gives me 8, I look at the 8, great, nothing's there. Go ahead and put 18 in. So nothing's happened yet, nothing. Now something's going to happen. 49. 49 mod 10 is going to be 9. I'm going to look down. Uh-oh. There's something there. Something already at that spot. So here's what I'm going to do. Here's my quadratic. I'm going to add I squared. And right now I'm at 1. So 1 times 1 gives me a 1. It says, hey, for right now, just move up 1 spot and see if there's an empty spot. And by God, there was an empty spot. I had to wrap around all the way back to 0. But yep, there's an empty spot. Put 29 in. Or sorry, 49. My apologies. Everybody okay with that? Now, pretend for one moment that there was already something in that spot. The next thing that I would do, this is the attempts. My second attempt, I would do 2 times 2, which equals 4. These are the spots I would move up. So now it's not just 2, because in linear it would go from 1, then to 2, then to 3. Here it skips 1, goes to 4. Hey, look at the 4th spot from the spot it really should be in. Does that fit? Now again, that's how this works out if we had another collision, but we don't. Next one's 58. 58 mod 8. Uh-oh. There's a spot. Okay. Now, 58, I'm going to start with 1. Can't put 58 there because 18, so I'm going to do 1. It tells me up to move 1 spot. Uh-oh. Can't do it. 89's there. So what I'm going to do next, I'm going to try 2. This time tells me move 4 spots. 1, 2, 3, 4. So notice, using that I squared, that's really all it is, quadratic, it's just saying how many attempts have I made to now how many moves am I going to make. So notice, pretend for a second, my third attempt. 3 times 3 equals what, class? Good. Bueller. Okay, you guys probably don't even know that damn movie. But anyway, so some of you don't even know Titanic. Anyway, so questions on that? Yeah, he has no idea what Titanic is. Yep, exactly. Any questions on that? All right. There's an exercise below this. I'm going to take a picture of this real quick. Yep, there it is. All right. Go ahead, do the exercise below. All right. Answer there is at the bottom. And again, you didn't have to get all the numbers in there. I'm sure you didn't, because there was a lot of them. But the positioning should at least be right. The position of where they were should be right. All right. So let me see your faces. Now, I need you to pretend something here for a moment. It's not going to be hard to pretend this. Pretend that you have a very, very large set of data that's coming in. Right now, what we've been playing with is chicken crap. You've been playing with 50 numbers, if that. 29, I think. What if we're housing every student at Texas A&M? Okay? And previous students. All of that information is stored somewhere. You better believe it. So, here's the neat part about this. Is in reality, the larger the data set, the more efficient this really becomes. So if you look at the example which I have here, and by the way, this is the funny part, is that in the examples that I'm giving you right now, it has a very low load factor. which means there's very few collisions. In real life, if you can believe this, a 20% compression, which is just 1 in 5, is actually considered outstanding. 20% is considered outstanding. So meaning that if you look at n, little n, that's 1 billion, that means 800 million of it is not going to have a collision, but 200 million is going to have a collision. And we'll look at a nearest prime, and I'll go over that here in a minute. Just 20% compression helps us tremendously. How many of you would like to have 20% faster vehicle? Probably most of us. 20% better fuel efficiency? Most of us. But what does this look like? And that's the picture at the very bottom. The picture at the very bottom, all of the vectors at the very bottom where you see the index number, 0 to, what is it, 18, 19, actually? Okay. And the data pieces are in blue. Notice, in reality, there's many of them that don't have a collision. They are by themselves. And then there's a significant portion in this example, 50% that do. But notice, it would knock down your sorting by almost a third. Or searching. I almost said sorting. Forgive me. Searching by a third. That's outstanding. There's one other thing I want to go over, and it's not in your notes. So bear with me for a second. I had a project like this. Oh, get the heck out of here. Oh, wow. Great. Another one. All right. So let me share this. Hang on. So white screens for you guys? Great. In every hash structure, we're going to have a bucket. We all know that. And that bucket is most likely some type of vector. Whatever we use for chaining can be any data structure we want. It doesn't have to be a linked list. If we are searching for something, what has been one of the best data structures to have when we're searching for something? Red-black tree or just regular binary search tree. Either one. Okay? But as long as you said red-black tree, that's fine. So imagine this. The bad part is, excuse me, because I'm dying up here, the distribution may not be perfect, but you could have your chaining end up in a BST or a red-black tree. Here you're breaking it into buckets, which is already a compression, and helps searching quite quickly. And then you add whatever's left over into a binary search tree. Damn, that's fast. So here was a project that I gave out one time. This was a phone book. And I gave them the entire data set for a phone book, which, by the way, was a lot. They only had to store the person's name and telephone number. That was it. And what I had to do is they had to devise a hash, table size, that would find the person within 20 tries, 20 probes. Sorry? It was, let's see, this is DC area, so it was probably 11 million. And by the way, every search they gave them found a person within 20 probes. Here's why. Their buckets was the first letter of the name. That already cuts down 26 possibilities down to 1. Now, was it perfectly evenly distributed for all of these? The answer is no. You know what the least, the letter with the least number of last names? I'm sure you can probably figure it out. X was one. Q was another. I forget there was a third one, so I was actually relatively surprised. Z actually had a decent amount, and that's because probably DC, Polish, a lot of Polish names with Z, Jewish names with Z. Man, it was a lot. So again, probably depends on the demographics. But think about it. I could find 11 million people in 20 probes or less. One person. It's outstanding. And damn near in constant time. Outstanding. So, hint, hint, this would be a question that you might have on that final. Might. This is the type of question that you'll get. It is probably 2 different data structures that if you merge them together, produces some amazing results. Okay? So just heads up now. Yes, sir. You do the average. You do the, because there's a Q, you would find the size of the Q and then find the size of the largest one, which is actually real short. And that's where you can find out your average big O. That's not hard either. That's the beautiful part. And again, as you know, with binary search trees, it's log of n, so it's even faster. So it's just amazing how fast we can really do that. Really is. But this is the type of question that you might get on your final. Just heads up. All right, oops. So that's the big picture of things, is that, again, you know, we're looking for this 80% compression. No. We're honestly looking for right around 20. 50% is great too. But it just doesn't happen that way in reality. It really, really doesn't. So here's what we're talking about, and it's a load factor. The load factor is basically a very simple division of how many buckets to the number of elements that you're really going to put in it. Now, you're also not always guaranteed that your elements have an equal distribution. Last names do not have an equal distribution. They just don't. Again, we just talked about Q's and X's had very little for last names. Okay? But at least we should be able to get some type of number that we know what it's going to be around. All right. So let me see here. What do I got? About 15 minutes left? Okay. So here's what I want you to do. So in this load factor exercise, remember that the chaining is what we're doing here. So I want you to calculate the load factor for this already completed example, and then what would be a better N for that. You know what? Nah, I'm not going to do that, because that's, yeah. You know what? I'm skipping that for now, only because it's not also going to be your new test. I know it's on your test, most of it. So let me get you something that is. All right. Here's something that is. Open and closed hashing. 2 terms. The only thing that's different about it is about how the actual data structure is done. In a closed hashing, think about it, all of it being stored within the vector. All of it. Whereas the open hashing, it still uses a vector, but the vector has pointers that are going out to whatever data structure that we're using. This one happens to use a linked list, but it could be binary search tree, it could be a heap. Who knows? But those items are the difference between open hashing and closed hashing. That's it, thankfully. There are pros and cons to all of them. Open hashing takes up more space. Just think about it. Not everything's shoved into the vector. Coding-wise, open hashing or open addressing is easier because there is some separation of state, key, and the chaining. It's not all shoved into one. Let's put it that way. So there is some goods and bads about overall of each of them. All right. So here's your first example of code, finally. There's your hash function. I know somebody's going to say, but that's in Java. I bet you can figure out how to do this in C++. That's why I don't change it. Notice there's two parts of that. There's the hash function, and then there's the compression function. The hash function, what it does is, it actually tries to make it into some kind of random value. It converts the characters into a very random set, and then goes ahead and then compresses or does a modulus on it. Now, why is it trying to put it into a completely random number? Why? Why?
It's more likely to get a better distribution that way.
Beautiful. It is. He said it's more likely to get a better distribution throughout our hash, and he's absolutely right. So, with that said, you'll see that 37 in there, and that 37 is not there on just by quinkydink. 37 is a prime value. So that's going to help us give an even distribution by putting in at least a couple of primes in there as we convert. So here's what it looks like. Let me do it this way. There we go. So what it's doing in this example, I don't think it did the prime. I think all it did was add it up. Let me just double check. Yes, that's all it did. So bear with me for a second. So all this hash, really cruddy hash function did was it just added up loopholely as ASCII values of 629, and then I hashed it, modulus 13, it gave me an index of 5, and that's where I put loopholey. Then did the same thing for Bucket, New York, Ocean Park, which is out in California. I did the exact same thing over and over again. Okay. Now, it looks like an even distribution, and that's fine at first, but here's the bad news, is that issues with summing string hash function. If the table size is large, how many strings are smaller and will be placed only in the first half of the table? So think about it. Think about three-letter words. But, the, was, stupid. Okay. Aren't all those not going to total up to anything big? And then you mod it, and you may end up not really having a mod. It might be just that number. And how many words are very small in the English dictionary? Most of them. They really are. So you're going to have a hash table that's really going to be very heavy on the low side. And how many of you can think of a word that has more than 10 letters long? So notice that bias creeps in if we don't do some type of manipulation with the number. We'll end up having a bias. So to get away from that, here's the better string version. And that's the exact same algorithm you just saw. Number one, it makes it into a massive number. And it's massive, so it has to be greater than the capital N. Makes it huge. So again, we don't have the bias of already being smaller than N, and there's no mod, it just shifts to that spot. We make it a massive number. Then we multiply it with a prime number. Prime numbers are not easily divisible. So that adds another aspect to it. Then we go ahead and do the green part and mod it and put it into its right spot. But notice we actually do a ton of work to make sure that our answers, or excuse me, our data values are placed into spots best as possible with an even distribution. So here's another example just below that. Notice, man, what does that say? 16, I think it's a prime number. Two of them there. There's 127. And then you see, I think it's 169 million. That's another prime number. So notice it makes this number massive just to make sure that it gets placed differently in our table. So there's a lot of work behind the scenes to try to make this as, frankly, evenly distributed as possible. Now, bad part is it's not that much work for you. It's work for the computer. That's the code for it, if you can believe it. That's it. It's done. All of it's done just that one shot. Was that a raising the roof? What are you doing? Go ahead.
Would this affect the overall effort for putting it in, though? Like, take away from some of the reason we use hash to begin with?
While true, would you rather search for something in a linked list? Just a straight up linked list. If it has millions of pieces of data. No. This easily makes up for that. So again, you've got to make sure it's a hell of a lot of data. So if you only have 10, 20 pieces of data, you're absolutely right. Not worth it. But if you have millions of pieces, and honestly, the computer does this calculation a lot easier than you and I think, and that's in your systems classes, it's not that bad. As long as it's a lot of data. It makes it way more efficient. Again, more data that it is, the more efficient it really is in the long run. But so there is a point. You're right. You're right. So here is what I would ask you to do if I had you create, hint, hint, a hash table ADT. There's nothing in there that's kind of nutty. We've already gone over it. You already know the hash table. You know how to search through a linked list. You know how to search through a binary search tree. That's contains. Insert, we just went over it. Remove, that might be interesting. Remove would be very similar to insert, but then you got to delete, and then what are you deleting from? What is your chaining data structure? Is it a binary search tree? Is it a linked list? That's not too bad either. So all of these items would be their different functions that you would create in order to make a very decent hash table. All right. I think I'm going to leave it right there. Oh, yeah. Here's one last one. It's double hashing. So in this, and again, I can't say I've actually had an application where this came up. Now, it's me personally. Dr. Tiagi may have. Who knows? Double hashing is doing just that. It's hashing it once, going through it, and then hashing it with another function that, again, you're praying gives you a very good and even distribution. So it's just basically going through two different hash functions to, again, hopefully get you a nice even distribution for when you want to find something. That's it. All right, I'll leave it at that. So everything that we covered on there, notice I skipped a few pages. That's fine. You're not responsible for that part. But everything that I did, that you will be having something on the exam with. Let's put it that way. Good luck on Thursday. May the force be with you. And I will see you guys then.